Hi, this video is going to look at halogens from the OCR A-level specification for chemistry. So in this we're going to look at boiling points of the halogens, electron configuration, trends in reactivity, disproportionation reactions, use of chlorine and precipitation reactions. So first up, we'll look at the boiling points. So halogens exist as diatomic molecules. So we've got fluorine will bond with another fluorine to form F2. Chlorine bond with another chlorine to form Cl2. Bromine with another bromine to form Br2 and I2. Now, as we're going down, our boiling points increase. Fluorine has a boiling point of about 75 Kelvin, so very, very low down. Chlorine, 238 Kelvin. Bromine, 332 Kelvin. And iodine, 457 Kelvin. So as we're going down the group, we're getting more and more higher and higher boiling points. It's getting harder and harder to break those induced dipoles between the molecules. And this is due to the fact that electrons are increasing. So the more electrons we have, the more London dispersion forces there are. You may know these as induced dipoles or van der Waals forces or lots of different names. I tend to use London dispersion force. But they're affected by the number of electrons. And fluorine, only 18 electrons, so very, very few number of electrons, few bonds form. Very easy to get it to boil then, because the bonds that are formed are weak. Chlorine, Cl2, up to 34 electrons, so we're increasing the number of electrons, so increasing the London dispersion forces, therefore the boiling point increases as well. Next up, look at electron configurations. So all halogens are in group 7. So fluorine has the electron configuration 1s2, 2s2, 2p5. So just one electron short of filling up that p subshell. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. So again, one electron short filling up that p orbital. Bromine is 4p5 as its final subshell, and iodine 5p5. So what this means is they all react in the same way, because they're all trying to gain this one electron to get up to p6. And they do this by adding an electron on to go to a single minus ion in what is a reduction, because they're gaining electrons. So the atoms gain electron, become either F minus, Cl minus, Br minus, I minus. And they can each do this with differing abilities. So we get a trend in reactivity. So I'm going to use Bohrs Model now to illustrate this. Now Bohrs Model has its issues and its problems, but for here, this particular example, it works quite well. So if we compare, once again, fluorine to chlorine. Now if we imagine bromine would be 4 of these shells, and iodine 5, and get bigger and bigger and bigger. They're each trying to put an electron here, each trying to gain one electron there. And so we're going to look at, well, who can do this the easiest? Because whoever does this the easiest can grab that electron. They're going to be the most reactive. This is the exact opposite of what we did with group 2. So group 2, they were trying to lose electrons. Group 7, they're trying to gain them. So what we're going to look at is, first of all, proximity to the nucleus. So the atomic radius. So fluorine, a lot closer. Chlorine, we get a bit of distance. The next thing we look at is shielding. And fluorine has little shielding. There's just that first shell. Chlorine, 2 shells, bromine 3, 4, and they're all bromine and iodine 3 or 4 shells shielding, and they're also getting bigger and bigger and bigger. So fluorine can attract an electron here really, really well for these 2 reasons. One, it's got a very small atomic radius, so the electron is very close to the nucleus, and 2, there's very little shielding. Now what chlorine, bromine and iodine do have going for them is that they've got more protons, so kind of a stronger magnet at the centre. But this is overridden by the number of the shielding and the distance. So fluorine is the most reactive. Then chlorine, then bromine, then iodine. This is because smaller atomic radius. It's closer here. Less shielding as well. So this creates greater nuclear attraction Now you may call them outer electrons, I call them valence electrons. So these are the electrons in the outer shell. Despite increase in proton number. This is overridden by the fact that there's smaller atomic radius and less shielding. So the fact that this has got 17 protons at the centre, this has only got 9, doesn't matter because these have much bigger effects on the ability to attract an electron into that orbital. So the reactions that occur, we don't really react with fluorine, don't like to use that in the labs. But we do reactions with chlorine, bromine and iodine. And we can see what happens when these react. So if we take a chlorine molecule and we react it with bromide ions. Now bromide ions, they're very happy. They've got that electron they want in their outer shell. Chlorine here, it's covalently bonded, but it would much rather be an ion. So it's going to come along and it's going to try and take away their electrons. And we know chlorine, from what we see, is more reactive. So it takes the electrons off bromine to become Cl-. Plus, then bromine has no choice. It goes into a covalent bond to form a diatomic molecule. So just to balance this, I'll put 2 and 2 there. And what we see in this reaction is a colour change. Because we've got bromide ions here that are aqueous, put that in, and now we've got bromine, which again, the aqueous but dissolved in water, we get bromine water. This turns brown because of the bromine that we've got there. Now, chlorine, if it's more reactive than bromine, it's certainly going to be more reactive than iodine, and the same thing happens. Now, in this reaction, iodine is like a black-brown, a very dark brown colour. If you want to differentiate between these two, you could add an organic solvent and you'll get a purple ring appearing with iodine. So if we tried to reverse this and go, okay, well, we'll take the bromine and try and react it with chloride ions, we get no reaction because the chloride ions can hold on to their outer electrons more. There's a greater nuclear attraction and the bromine can't take them off them. But bromine can take them off iodide. Which again would turn black and brown. So they're the displacement reactions, we call these, where a molecule steals the electrons to become an ion. And if it's more reactive, it will accomplish that. So next up, we've got disproportionation. I'm sure I pronounced that properly, and I always spell it wrong. Disproportionation. So, in this reaction, well, in a disproportionation reaction, an atom becomes both oxidized and a different atom of the same element becomes reduced. And halogens do this, specifically chlorine, when it's added to water. So take chlorine gas, add it to water, we'll bubble it through, we get HCl, aqueous produced, so hydrochloric acid, and HClO, aqueous as well, hydrogen chlorate. So if we check the oxidation numbers here, we've got chlorine that is here 0. Got hydrogen +1, oxygen -2. Over here in this, we've got hydrogen at +1, and one of our chlorine atoms then must go to -1. So we've got chlorine going to Cl -1. If it's become -1, it must have gained an electron. If it was 0 here, -1 there, it's taken an electron. So here we've got reduction. It's gained an electron. Over here, though, oxygen always -2, except in peroxides. Hydrogen nearly always +1, except when bonded to a metal. So -2 and +1. Chlorine here must be +1. So we've got chlorine 0 going to chlorine +1. And that must have lost an electron. So that is oxidation. So chlorine is being reduced and oxidized in the same reaction. And that is what a disproportionation reaction is. So uses now. Chlorine used in bleach, but it kills bacteria in water. Chlorine, really good at killing bacteria. However, there is a downside to this, that it's toxic and can cause some damage to humans, especially in high concentrations. It can also damage the environment, but we generally think that the positives outweigh the negatives in this one. So, final part of halogens is precipitation reactions. Again, another word I'm bound to spell incorrectly. I think I've got it right there. And if we take the ions of our halogens and we're going to react them each with silver nitrate, and what we really want is just the silver ion here. So we're going to react chloride with silver, bromide with silver. Just make a note up here that it's with silver nitrate is the compound we use here. Bromide with silver and iodide with silver. We get 3 different products. Now, at this stage, they're all aqueous. But the products they form are solid. So Ag++ Cl- goes to AgCl solid. And this is a white precipitate. Notice that it's become solid. If you ever have to draw one of these equations, you will have to include the state symbols. Silver bromide's formed in the second one. This is a cream precipitate. And silver iodide is formed in the final one, which again is solid precipitate, and this is a yellow precipitate. So often difficult to tell white, cream, yellow kind of apart. Maybe if you had chloride and iodide, you can kind of spot the difference between them. So what we can do with this product is try and dissolve it again. And now we know it doesn't dissolve in water, because this reaction kind of says it, but it will, or some will, dissolve if we add NH3. And silver chloride really is very soluble in NH3, so if we just use dilute NH3, then it's soluble. So add a few drops of NH3 after you've done this reaction, If the precipitate dissolves, then you know it's the chloride. Now, if you have to switch to a concentrated NH3, so maybe you've added a few drops of the dilute and it's not really dissolved, so then add a few drops of the concentrated NH3 and then it dissolves. Spell all the difficult words right, but then soluble I spelled wrong. If you add conc, then it dissolves, then you've got silver bromide. And if you add conc NH3 and it stays a precipitate, so it's insoluble, you've got silver iodide. And that is the halogens from OTRA level chemistry.